So welcome. I should have done this presentation with Valerie, but unfortunately he got sick yesterday, so I'm here alone. Me and Valerie, we work for HydraDX. You might know HydraDX. It's basically a DEX on Polkadot. And today's topic will be, or today's topic of this little workshop here, or tech talk, will be fuzzing, right? Fuzzing is a hot topic these days. Everybody wants to do fuzzing. So we will just do a brief overview. Initially, this was the part which Valerie should have done, and I should have done the live demo. So I will do a little bit of talking about fuzzing, what is this fuzzing, but we will focus mostly only fuzzing substrate runtimes. We will not go into detail what fuzzers are, how they work in the under the hood, because that's out of the scope and outside my knowledge, to be honest. So we will look at one specific fuzzer, which is developed by SR Labs, Ziggy, and substrate runtime fuzzer. And then we will look at some ways you can optimize the fuzzing to help the fuzzer a little bit, because as we will see, if you do just some dumb fuzzing, as we call it, then it doesn't always reach all your codes you want really like to fuzz. So what is fuzzing? So as a brief overview, you can look at it as automated testing, which generates never-ending streams of random inputs and throws it at your API. So in our case, in case of substrate or runtimes and palettes, are the extrinsics, right? That's the public APIs that can be called by anyone. So it helps you to detect corner cases. For example, it can help you detect a panic in your code that you maybe didn't even know about it's there, or maybe you knew there was, but you didn't think that it could be reachable. But maybe the fuzzer can help you find a case or the conditions under which you can reach this panic. So to set up the fuzzer for substrate runtime is actually surprisingly very easy using the tools developed by SR Labs. But out of the box, it will be quite dumb. It will just throw some random inputs. It will try to find your extrinsics that it can call. And it uses so-called coverage-guided fuzzing, so it helps you to show you what it can reach and how it can reach it. And it can help you to find some roadblocks, right? And then you can look at it, and we will see in the live demo how you can detect how far it can go, the fuzzer, and then you can do some things which helps the fuzzer go a little bit further than that. So there are many different types of fuzzers. This is a snapshot or screenshot of a post in Polkadot forum, I think, but we will just focus on the last one, which is the substrate runtime fuzzer. So this is built on the top of Ziggy. Ziggy is, again, developed by SR Labs. We had a 2 days workshop with them. So that's why we decided to do this presentation today as well, so to share our experience. So, and what we learned. So Ziggy it's not substrate specific thing. It's, we can call it multi-fuzzer management tool, which uses different fuzzers under the hood and helps you with the monitoring of the instances of each fuzzer, and helps you to discover the crashes. And it uses AFL++ fuzzer and HonkFuzz fuzzer implementations, and then it does the coverage-guided fuzzing and all these seed mutations. We will look at it a little bit in detail later on. So what is this good for? The fuzzing is good for, as I already mentioned, for the reachable panics or unsafe arithmetics mainly, right? For example, you do some calculations in your code where you do A plus B, and you think that, okay, these values are not going to be so huge that it can overflow. but Fuzzer can help you find a case where it can overflow, and as we know that if you use unsafe arithmetic, it will panic, and if you panic in runtime, in Polkadot sub-thread runtime, then it's a problem. But it doesn't really help you with the logic, business logic that you have, because it doesn't know. It doesn't know what your application is doing, should do, and if the output after you execute something is correct or not. But you can help him a little bit, right? For example, if you combine it with invariants, right? So let's take our case, right? We have the OmniPool implementation, which is a type of IMM on Hydra, right? So in IMM, you have, for each IMM type, you have different invariants you can define that must be respected, must hold after a certain operation is executed. For example, you execute a trade, and the invariant must, for example, not decrease, right? Because if it decreases, then you leak some value from your M. So the process is to set it up, like I said, it's quite simple, and it's sorry. And it's pretty straightforward. You give it some parameter how many threads it can use, and it starts so many fuzzing instances in parallel. It uses the AFL fuzzer and the HonkFuzz fuzzer, and then it monitors all these instances and for crashes, right? For the seeds, for everything. It has one shared corpus. That means all the seeds it uses, it's shared between all these instances. So each instance of the fuzzer can pick up, can choose the seed from one seed or input queue, right? It helps you also triage the crashes. So if it detects multiple duplicates, it can just report one, and it generates the coverage. And I already mentioned that using the coverage, you can discover what roadblocks it has, and then you can decide how you want to solve them. So this is just a brief overview of what fuzzing is. So now you might be asking, like, how does it work, right? So I started, but I have no idea how does it work under the hood, right? So we will look also at the implementation briefly. But the architecture of this would be something like this. So you start with the seed pool, right? The seed is just something that can be executed on runtime, right? So let's say an extrinsic with some parameters, right? So it chooses some of them, and it generates one seed, which will be used as an input for the next iteration, right? Because the fuzzer is continuously running and in a loop, and it executes different fuzzer with the same state, right? Then this generates an input, and the input in our case, in your case, it might look different, but I think if you take this template and you start creating your fuzzer, you will do something very similar. It can look like this, right? So now you look at it and you said, what does it mean, right? So I was baffled at the beginning when I saw this for the first time. I didn't know what does it mean. I have no idea. For me, it's just a bunch of letters and numbers and asterisks. But these asterisks are actually not meaning that, okay, there can be some additional numbers. This is our delimiter, right? So the fuzzer will generate something like this, and it will also generate these asterisks. It's 8 of them, I think. So this basically divides the possible possible calls that can be executed. So this can be translated to something like this, right? So the input will be like we see, and after it decodes what it means, it will decode it into 3 separate extrinsics that will execute in one iteration, right? So first one, like swap 5 dots for HDX in OmniPool. Then after that, it will execute the next one, which is transfer 10 dots from Alice to Bob. And then it will execute the stake 1,000 HDX in our staking in OmniPool. So it takes this input and it runs against a target, right? So in our case, it will be the runtime. And let's say there were no crashes. So now, what does it do with the input, right? So if there was a change of coverage, so it finds something that one of these extrinsics went a little bit further than the fuzz reached before, it adds it back to the seed pool, where the next iteration or even the next instances of the fuzzing can pick them up again and choose it and chose them for the next input. If not, then it simply drops it, right? So because since there was no additional things that changes anything that was previously covered, it can simply drop it. So this is how it works a little bit under the hood, right? So now you have your runtime and you need to set a state, right? Because we know each parachain or each chain has some kind of state. This you can do in multiple ways, right? You can use the Genesis block, the Genesis builder to define your state, and if this is okay for you, you can just use that. But for our case, it was a little bit different because we cannot really set up Hydra as initial states that we want to fuzz against, right? We want to set up the omni pool, we want to set up the stable swap pools, and we cannot really do it with the Genesis, right? So we develop little tool which basically takes a snapshot of the mainnet and simplifies it and saves it as snapshot externalities on the disk, and the fuzzer will load them and use that as an initial state which will fuzz then against, right? So now we will look how the fuzzer is actually implemented. It's pretty simple, right? Not many lines of code. And it's a simple program, right? It has an entry function, main function. And then the main entry point for the Ziggy is this Ziggy fuzz macro. And this parameter data is the data what is provided by the fuzzer, right? The random input data. So then we put it into this structure, which is simple structure, which takes the data, and it implements the iterator. And as I talked about before, the asterisks are actually the delimiter, right? So if you look, the delimiter is defined somewhere about here. So, and it basically splits the input into several possible extrinsics. Somewhere here it goes through this, right? Iterable. So it takes the first input, which will be any number of bytes, right? Delimit it by the delimiter, by the first part. And okay, so now you can use this as an input and you can try to decode it as an extrinsic. But you can also do some other things, some very fancy things with this, because you can say, okay, the first few bytes I want to use for something else, right? So we decided we want to have an information or a case where we want to skip some blocks before this extrinsic is going to be executed. So we say, okay, the first bytes of the input will be used as a lapse. This will give us information how many blocks we want to skip before the extrinsic is executed. Then the next 2 bytes will be the origin. The origin will be, okay, this is the origin who is going to execute this extrinsic, right? So because you want to have random account that is executing extrinsic, you don't want one account executing everything, so you can set up various origins, and these 2 bytes here will determine like which origin the fuzzer will pick up and execute this extrinsic width, right? So you can have we have random 20 accounts funded, right? And then you can also set up various other origins which can execute, which has a more power, right? So you have, for example, something which can be executed only by some certain origin, right? So you can set up this, and you say if the origin here, these 2 bytes is like 50, for example, the fuzzer will pick up that instead of some random accounts from the first 20. Okay, and now the structure. So this we didn't have initially in this 1 byte in our first iteration of this fuzzer, but then we realized after looking at the coverage, which we will see soon, that it took some time to find the correct parameter for our needs. For example, for omnipool, for a trait, for the cell, it took some time to find the correct asset IDs, for example, that you can trade in omnipool, because asset ID in our case is 32-bit integer, right? So it has many possibilities, a big range to choose from. So, but we have only 15 or 20, maybe, assets in the omnipool. So we can, the correct ones are only 0 to 20, right? So we say, okay, we will help the fuzzer a little bit in this way, that if this 1 byte is something that we want specifically to handle, then we will do something like this, right? So we say if this 1 byte, let's look at the omnipool helper here downstairs. Oh. Okay, here, right? So we say if it's 0, right, the byte we saw above, if it's 0, then we will execute the cell, right? So that means we take this information provided by the fuzzer, the 1 byte is set to 0, and we say, okay, this will be the cell, and which we select the assets from the assets which we know that are already in the omnipool, right? So the assets will be always correct. So it helps the fuzzer find the seeds that will actually reach the code a little bit further instead of the fuzzer trying to find and taking some time to find that he can choose only from 0 to 20, right? So we say, okay, the first byte will be some random byte determining which is the asset in, which is the asset out, and the rest of the 18 required bytes will be the amount, right? The amount in our case is 128-bit integer, so 16 bytes for the amount, and it will just say, okay, this is the omnipool cell. But okay, so now you might be asking, okay, so now we are just telling fuzzer use this to do the cell, but this is not the only way that he can generate an input that will decode into the cell, right? If this helper byte is not a 0 or it's not 1 or whatever we use specifically, it can still decode the extrinsic into the cell operation with random assets, random parameters, right? As we can see here. So we now have, okay, this is the input we were talking about at the beginning before. So he takes the first bytes and detects the labs, decodes the labs origin and the specific extrinsic, and the rest of the bytes will be the encoded extrinsics, which will try to decode with the codec, right? If it decodes successfully, that means it's something it can execute, and it put it into the list that it can execute, right? So, and then it goes into the next loop where it executes these extrinsics one by one, right? And basically it starts the block. Then if there was the labs, it skips certain amount of blocks. It takes care or tracks the weight, because we don't want so many extrinsics that block will be overweight. And then it finalizes the block, executes the extrinsic, right? It dispatches it, and it finalizes the block. And this is the result. As I said, he doesn't care what is the result, because the fuzzer doesn't know whether the result is correct or not, right? So, so this is the implementation. It's very, very simple, right? You can use this. You can just provide your genesis, and it will work, right? You can fuzz this with your against your runtime. So now let's do the live demo. That will be the best, because we'll see this in action, and we will see also where in the code, where in the palette you can put certain assertions to ensure that the business logic you have is correct. In our case, it's the invariant of the AMM. But yesterday, when I was preparing this demo, I realized that this machine is not powerful enough to do the demo at the end. So what I want to do is basically, I want to start the fuzzer right now without any prior attempt to run it. So without any knowledge that the fuzzer will have to find an issue in our Omnipool implementation. And I want to demonstrate how long it will take him to find an issue. So what kind of issue we will be trying to find? So IMMs, there is always a lot of math involved, right? There is various formulas, calculations, and there is also a lot of mistakes that people can make. So one of the mistakes, most common I would say, which were exploited in the past a lot, is the rounding issue, right? So we will try to find a rounding issue using the fuzzer now, and see how long it will take to find it. And then we will look at the crash report, and we will also generate the coverage to see how much other stuff he did in the few minutes we will run it right now. So this is our buy implementation in Omnipool, right? And this is the calculation of the state changes that it needs to be done. That needs to be done after when you execute our trade, our buy. So buy tells that you specify exact amount of asset you want to get out of the pool, and these things here must figure out how much asset in you have to provide to be able to get the asset out. So there is some rounding involved in this. So we see that we add 1 here. So we will just comment it out. And we also do some rounding here, right? So we'll comment it out, and we hope the fuzzer will find this issue, right? So because now the rounding is not correct, because here this means this is the amount the user have to provide to be able to get the exact amount of asset out, right? But we rounded it incorrectly. In IMMs, you really want to round in the favor of the pool, but if we don't round this up, that means we round in the favor of the user, right? Because when you look at this calculation here in detail, you see that we do some division, so there is some remainder, right? So that means without rounding this up, that means you ask a little bit of a less amount that the user have to provide to be able to get the amount out he wants, right? So this will be the fuzzer running. So it generates the output directory to make sure that I'm not cheating. I will delete this directory. In this directory, he stores all the seeds, all the whole corpus, all the seeds, all the crash reports of the previous runs that he can use also for the next run. So there is nothing he has right now. It starts from the scratch, and we will see how long it will take to run, right? So we will run this. It's a very simple command, right? Cargo ziggy fuzz, and then you specify how many threads you chose, only 2, right? So because this machine will now heat up and probably catch fire. But so this is the output of the Ziggy. It tells you that it's running for 15 seconds now. It does only 500 execution per second, and it already did, how many it is? 8,000 executions, right? But if you run it on a decent machine, you will see thousands of executions per second, right? And if you run the honk fuzz as well, because this is only the AFL fuzzer, you will see some similar input underneath, and it will run in additional instances. So I'm running just 2 threads here. So we will leave this running now, and we'll see if it finds the issue. In the meantime, that I will show you now where you can define your invariant in your code. So to detect this rounding issue, the IMM has some form of invariant, right? So we have a separate repo in our repository where we define our invariants, right? So for the omnipool, we say that after the swap, this must hold, right? So that means if R is the reserve of an asset, Q is a reserve of Lerna for that asset in the pool. Lerna is the hub asset, which is minted for each asset in our omnipool. So if you take the old state, which is the RQ, this must be less than the RQ plus, right? If it's not less, that means you have some issue in your calculations and your invariant doesn't hold, it's actually decreased, and that means you leak value somewhere, right? We have a bunch of other invariants for each operations, right? Also defined. Here you can look at, if you want, it's a public repository. This is on the function level. So what you want to do, you want to tell the fuzzer that you want to check this after the buy is executed, right? So this is buy extrinsic implementation in omnipool palette. So it does a bunch of stuff, right? And then at the end, I simply edit something like ensure trade invariant. So, but you don't really want this to be part of your production code, right? So you can hide it behind try and runtime features because substrate runtime fuzzer builds your runtime with try runtime features because it takes advantage of certain features it provides. And one of them could be also that you can stick these little checks in here, directly in your extrinsic implementation. And then I simply implemented the invariant which we saw here, just simple implementation here, and we do the assertion. So we don't really want to have it in the production because we know that assert will panic. We don't really want to panic in production. So we will hope that our fuzzer, which is running in the background, will actually hit this assert and it will fail because the invariant shouldn't hold in this case, right? So another thing you can do, we call it like palette level, system level, is take advantage of the try state hook. You may know that palette has hooks you can implement, right? And like on finalize, on initialize, and so on. And one of these is try state, which is also behind the try runtime features, and it's executed after the block is finalized. So after each block, it will go through all your palettes, it executes this, this hook. And here you can also basically tell the fuzzer, okay, this is what I want to check after everything is done, right? So some form of another thing, right? You want to check the storage is correct, the state of your palette is correct, and everything after all the extrinsic were executed in your iteration, in the fuzzer one iteration, right? So what we do here, this is just an example. In omnipool, what we do is that each token has some amount of alerta minted, right? And we store this information in the storage. That, okay, dot, for example, dot has this amount of lerna, HDX is the amount of lerna. So if you sum this all up, it must equal to the balance of lerna in the omnipool account, right? Because if it does not, if it would be, for example, less, that means one of the tokens has more lerna than it should have, and that means it works with incorrect values. No, this one. All right, okay. So we now see the red cache is saved, right? right? It already found many crashes, 11, right? So hopefully it only found the problem I just created in our omnipool, because if it found something else, then I might run away now. So I mentioned that it creates the output directory, and in the output directory, it stores many information, right? It stores the corpus, which are all the seeds it uses. Then it stores the crashes, logs, and so on, right? So if you look at the crashes, so this is let's take 8, right? So this is one of the crash it found, but if you look inside of it, it doesn't tell you much, right? It's just a bunch of nonsense, right? So how you can investigate this crash now, right? So Ziggy has a command called Ziggy cargo Ziggy run, and you can give it an input, which will be the crash report. And it will run the crash report, and it will tell you what happened. So we can see that it executed buy with these parameters. It tries to buy asset with ID 100, and it tries to sell asset with 220, and it tries to sell this amount of asset. It tries to buy this amount of asset out, right? And we see that it hit the problem, it hit the crash, as we expect, because of the rounding issue, right? You see that this RQ is slightly less than the RQ plus. That means the invariant doesn't hold, and that means you have a problem. It doesn't necessarily mean you have a rounding issue, but you might have some other calculation problem. So you need to investigate, you need to look at your code where it goes wrong, right? Where it went wrong, and identify your problem. So after you fix, you can rerun. Basically, after you fix the code, you can rerun the same code with the crash report, and it won't fail again. It will say that now it was correct. So how long it took to find it? It was a couple of minutes, right? So I started, it was 30, yeah, around 10 minutes, and it already found 11 crashes. So pretty good, even of this slow machine here. So and now final thing which I would show is the coverage report, which is generated by another Ziggy command, which is the cover. It basically goes through all the seeds that it executed, all the inputs, and it generates some coverage report. It just give you the output is a simple web page which tells you, and I will show you that what it reached and how can you identify the potential roadblocks for him that it cannot go through without your help, right? So this will take a little bit of time. So it's already mentioned, and that would be all. So let's look at the cover. Yeah, it's still running because it was running for 10 minutes. So in the meantime, any questions? Yeah.
Hello. Yep. So how's the coverage being done? You have like instrumented the code manually, or?
Yeah, we will look at the coverage right now. So I don't see. There you go. So it generates something like this for you, right? The numbers will be always very low because it won't go any further than this, right? So and you can just look what you are interested in, right? we are, let's try the omnipool, right? And you can see that it hit some storage, right? No errors, some errors. And let's be in, okay, these are the extrinsics, right? So he also managed to actually add a token to the omnipool, which would probably be done by the initial state. So this is not interesting at the moment. So add liquidity. You can see that it tries 15 times to add liquidity, but it manages to go through only a few times, right? Most of the time, it hit a problem somewhere here that it. No, this was okay here, right? So the price barrier was incorrect, right? So this is something the omnipool implements, which is out of scope of this, but we see they didn't hit remove liquidity at all, right? In the 10 minutes that we were running, it didn't find any input that will hit remove liquidity, but it's actually found sell, right? Sell found 100, 200 times. Yeah, this is a little bit confusing. So, but 66 times it went through, and it hit a lot of times. It hit also this error, not allowed, right? So, but it was also successful quite few times, right? And then the buy hit also a few times, but this was also due to the help that we gave it with the structured fuzzing, right? So, and then you can look at the other stuff, but it will be always red. I can guarantee you that. But as we were told, we shouldn't look at the numbers. We should look how further it went and what we are interested in. How can we help the fuzzer go a little bit further in the areas we would like? So yeah, so that would be our presentation for today. Hopefully it was somewhat interesting. If you have any questions, just ask now or find me later, and we can discuss.